Hello class. Today we're going to do sequential circuit design. We're kind of jumping ahead to chapter 7. I'm going to kind of give you the condensed down version of the chapter, and really everything boils down to this. You can get into some different techniques talked about in the book, and I do encourage you to read the book, but this is going to get you to where you need to be for homework 6. So homework 6, quiz 6, and lab 6. So the problem we're going to tackle is design a circuit to count 0, 2, when x equals 0, and 1, 3, 1, 3, ... when x equals 1. X is a switch or an input to the system. So you want to save this method. You're going to use it over and over again. Previously, you would have had to memorize it for the test, final exam, but now you can just refer back to it and use it. 1. Encode the states. So if you remember back to our introduction to sequential systems, we had to kind of come up with our states. Here our states are just kind of handed to us. We're going 0, 2, 0, 2, 1, 3, 1, 3. So those are our states. And we're going to do these all step by step. I want to just give you the whole process first, and then we'll refer back to this. Next, you do a state diagram / graph, state graph. Then you do the state table. Lab 6, you also do a truth table. So I'm going to call this 3B over here, and this is 3A here. So that's all not new compared to the last couple lectures. Now this is new. So you're going to go back to 3A, add columns for the flip-flop inputs, and fill in the columns from the flip-flop design table. And like I said, we're going to do all these steps for this problem up here. You then do K-maps for all flip-flop inputs. And for the truth table in step 3B. And then 6, you build the circuit. All right, so just as a reminder, x equals 0, we go 0, 2, 0, 2, ... X equals 1, we go 1, 3, 1, 3, ... continue. Well, like I said, these are given to us, so 0, we just encode these in binary. I did them out of order just because I was thinking about the sequence. I mean, you could also write them like this. Notice that the mapping here is the same. 0 is still 0, 2 is 2, 2 is 2, 1 is 1, 1 is 1, 3 is 3, 3 is 3. It's the same thing. Now in Lab 6, you can still use this mapping, but as a note about Lab 6, your state, Q2, Q1, Q0, are inputs to circuit to go to 7-segment display. And if that doesn't make a whole lot of sense, don't worry, I'm going to do a Lab 6 walkthrough. I'm just pointing that out. If you get all this, that can be the last key on how you connect what we're doing now with Lab 6. Lab 6 is a combination of this new stuff plus really Lab 5. Okay, next, state diagram. Well, we go from 0, go to 0, we go to 2, go to 0, we go back here. We have a 1. If we're in state 1, we go to state 3. We have a 1 as input, and back and forth. What if we're in state 1 and we get a 0 as an input? We jump over to this sequence. Same thing, if we're in 3 and we get a 0, we're going to jump to the start of this sequence. If you read Lab 6 carefully, that's what it says. If the input changes while you're in the middle of one sequence, you jump to the other sequence. So likewise, if we're in 0 and we get a 1, we jump to the beginning of this other sequence. And if we're in 2 and we get a 1, we jump to the beginning of this other sequence. So here's our state diagram. So next up is the state table. So fill this part in just like a normal truth table. Over here we have our next states. Q1 next, Q0 next. So this you take from your state diagram, or just think about how the problem was set up again. Remember, from state 0, we're going to state 2. We go 0, 2, 0, 2. So when the input is 0. So 0 goes to 2. 2 also goes back to 0. If we're in state 1 and we get a 0, we go back to state 0. Pull this up here. You can see it. If we're in state 1 and we get a 0, we go back to 0. If we're in state 3 and x is a 0, we go back to 0. Remember, these are our X values here. Inside is the state / the output. And in this case, the output and the state are the same. We're just encoding it into binary. If we're in 0 and our input is a 1, we go to state 1. If we're in state 1 and our input is a 1, we go to 3. If we're in 2 and our input is a 1, we go to 1. And if we're in 3 and our input is a 1, we go to 1. So this is just like a truth table. These are your inputs. You can think of them as kind of like your inputs. These are from the state graph. And this is step 4 from the design table. Let's use JK flip-flops. You could use any type of flip-flop. Sometimes you're told what to use. Sometimes it's left open to you. I'm choosing JK because that's what I recommend you use in the lab. In the real lab, physically, we have JK flip-flops and D flip-flops, which you could use either one. On Logisim, we have all 4 types. In this case, I'm just going to use JK. So, J1, K1, J0, K0. So these go with Q1, and these go with Q0. Here's the design table. And I'm just copying it from my notes. Normally I would tell you need to derive it. But you'll just be able to look in your book and do it. So we have this. We have a Q and a Q next. We need to know how to set J and K to achieve this. This is what we want our circuit to do. We want it to go from this to this or this to this, as defined over here. How do we set J and K? Well, that's what the design table has told us. So, here's where I'll oftentimes cover things up so that I don't get confused. Make sure that you're just comparing Q1 with Q1 next. Ignore the Q0 columns. And you could even cover up this over here. It's going to make it difficult for me to write, so I'm going to leave it open, but you know, we're filling in J1 and K1 from Q1 and Q1 next. All you do is take these 2 values and look up the appropriate row over here. So here we have a 0 and a 1. 0, 1. 0, 1. So that means we need to set J and K to 1 and X. Here we have a 0 to a 0. That's the first row, 0x. Here we have a 1, 0. 1, 0, we take x1. 1, 0 again. I don't need to look it up, but there it is, x1. 0 to 0, 0x. 0 to 1, 1x. 1 to 0, x1. And 1 to 0 again, x1. So again, I take this pairing, keep the subscripts the same, look up these two values, pick this row from over here, 0, 1, to give me this value 1x. 0, 0 is row 0, 0 here. So I take 0x from the table and put it in here. Now we jump over and do Q0. So 0, 0 is this row, 0x. 1, 0 is x1. 0, 0 is 0x. 1, 0 is x1. 0, 1 is 1x. 1, 1 is x0. 0, 1 is 1x. And 1, 1 is x0. And I'm double checking to make sure I got this all correct, because I did it without looking at the notes. It's easier to explain it when I'm focused on this page. But yes, everything looks right, assuming I did it right a year ago, even though this problem is slightly different from a year ago. That looks good. If we were going to put something up on a 7-segment display, then we would have something like this. You know, we'd set 0, 0 to be this, this to be this. I didn't say that we're going to do that on this problem. We're just focusing on the new stuff, the flip-flops. But here, the state replaces your switches. Like I said, we're not going to do that on this one. I will do an example when I do a lab walkthrough. All right, let's see here now if I can get all this up at once. J1. Here's K1. This will be J0. It is perhaps a bit tedious to fill all these in. All right, so 0, 0, 0 for J1 is a 1. 0, 0, 0. Here's my X, Q1, Q0, 0, 0, 0. I take the 1 here. 0, 0, 1. 0, 0, 1 goes right here. 0, 1, 0. 0, 1, 0. Notice we have to skip right here. Because remember, the order is different on the K map. And then 0, 1, 1, 0, 1, 1. This X goes here. So I'm going to put a little arrow here just to note that we flipped these. Now let's do the bottom half now. This is 1, 0, 0, 1, 0, 0. So the 0 goes here. 1, 0, 1, 1, 0, 1. So put a 1 here. 1, 1, 0. Notice here 1, 1, 0. We have to skip down to the bottom box here. And then the last line, 1, 1, 1, the X goes here. So again, we swapped. You can do these really quickly, and in a test situation, that can be really helpful if you just go down the column and switch these two. In this case, they're the same, so there was no switching. So this first row is X, X, 1, 1. So try to watch both again. We go X, X, skip, 1, 1. I didn't skip because it went the same there. Again, X, X, 1, 1. X, X, 1, 1. Just looking ahead, we're going to get to this, but hey, that one's nice and easy. That's a 1. That worked out nice. So let's use that trick again here. 0, X, X, 0. 0, X, X, 0. And then we have 1, X, X, 1. And over here we have X1, 1X, X1, 1X, and X0, 0X, X0, 0X. If you can't fill them out that quickly, you know, again, I'm not expecting you to get this on the first try. Rewind, watch it, watch carefully. Try to go slowly, at least on the first few, and point out how that goes. Practice it a little bit. I've had 5 years of practice doing this, so you're not going to be as fast as me most likely, and that's okay. You're going to have plenty of time to do the test or the exam, so it's best to work carefully. Notice here for the J's and the K's, we took all 3 inputs here in our K-maps. For Lab 6, you'll have J2, K2, J1, K1, J0, K0, X, Q2, Q1, Q0. So you have 16 variable K-maps, or 16 min-term K-maps. 4 variable K-maps, size 16. So, step 6. Circuit. Well, J1 is equal to, looks like we've got to take these two and these two. So it gives us XQ0 or X naught Q0 naught. K1 is equal to 1. J0 is equal to X. K0 is equal to X naught. There's something really neat you can do if we were doing this in the lab, and that would be to put this on PLDs. We can't do that in Logisem. There's really no concept of PLD that I'm aware of. Maybe there is. There actually would be a way to kind of simulate it, but we're not going to do that. So I kind of suggest you use the encoder for Lab 6 to drive your 7-segment display. So again, talking about thinking ahead for Lab 6, not encoder, decoder. And the outputs from the decoder go to the 7 segment display, much like Lab 5.3. You can also do it like Lab 5.1 and just use AND and OR, NOT gates, or NAND gates, however you want to do it. Alright, now I'm going to attempt to do this on Logisim and hopefully make it viewable for you. Alright, so I'm going to need a clock. I'll need not arithmetic, but memory. JK flip-flops. I'll label this one Q1. So Q0. So there's where we should see our counter going once we've done this correctly. In Logisim, you don't have to worry about the enable or the clears on these flip-flops. So in the last lecture, I hooked those up, but I'm not hooking them up here just to save time and because I don't need to. All right, so Q1, this is J1. This is the most complicated one. J1 is XQ0. I need an X here as well. Narrow, 2 input, so we have X and Q0. This is going to be kind of sloppy. And then over here we have X0 and Q0. Oh, I wish I could extend it upwards. See if I can pull everything down neatly. So I'm going to need that X0 again. So other one is X0 and Q0 not. All right. K1 is a 1. Easy. This is easier than Lab 6, but this is our first introduction to this design. So it can be tough to see the whole process too. So that's why I give it to you in a step-by-step fashion. Just do it one step at a time, trust the process, and as you do it a few times, you get more used to it. J0 is equal to X, K is equal to X0, K0 that is. Control K enables our clicks. So we're going 0, 2, 0, 2. Now I should go 1 and 3. That should take me back to 0. From the 2, I should now, because I'd change that to a 1, should go back to 1. And this should jump me back to 0 now on the next click. Yeah, so there you go. Circuit works. So again, I will do a Lab 6 walkthrough. I've said that a couple times, I believe, but just so you know, for Lab 6, this is what's going to go to your 7-segment display. So instead of switches moving through your 7-segment display, like it did for Lab 5, you're going to have these states moving through your 7-segment display. So that's all I've got on this topic for now. It's the same process, whether it's a D flip-flop, a T flip-flop, or an SR flip-flop. The difference is that you use a different design table. And so that means in this step here, instead of using J's and K's and this design table, we could use S and R in the SR flip-flop design table, or D flip-flop. You can even combine. You could have used a T flip-flop for this and a D flip-flop for this one. Again, this is the flip-flop we chose for Q1, the one we chose for Q0. So, but that's the process right here. Always refer back to this. If you're unsure what to do on any of these steps, that's where you do. Don't move ahead until you've got each step done. You have to do step 1, then 2, then 3, on down. All right, thanks. I'll see you all soon.